Welcome back, everybody. Today we're going to get going with Chapter 10. And Chapter 10 is all about advanced algorithms. Basically, what we're going to do with this chapter is take a look at some of the common ways programmers search and sort data sets. We're going to talk about how those algorithms work, why they work, how to implement them, and then also we're going to compare and contrast them to look at advantages and disadvantages of each type. Okay, this chapter is going to be a little different in that we're not going to be the ones writing the algorithms. We're going to, for the most part, just be studying them. And in 10.1, first thing we're going to look at is a search algorithm called binary search. So before we talk about binary search, let's look at something a little simpler that we can call linear or sequential search. Okay, now this is something we've actually been using all semester long to search through arrays, array lists, and even 2D arrays. Okay, let's look at a simple implementation. Okay, we want to search, in this case, an int array of nums for an int we'll call value. And basically what we do with linear search is just loop through the array from index equals 0 to length. So in other words, all the way through the array. And if we find the value at nums I, we're just going to return that index, return that I. If we don't find it, we'll return a -1. Okay, again, this is something we've been doing all semester long, whether it's to count the number of occurrences or search for a value like in this case. Basically just looping through an entire list, looking at spots one at a time. Now, linear search is great because it's simple. And also in a lot of cases, it's the best we can do. It's really the only search algorithm available. Okay, however, if we have a list that's already sorted in numerical order or even alphabetical order, linear search isn't the best way to go. Okay, think about searching through, let's say, a dictionary where we know all the words are ordered alphabetically. It would be silly to start on page 1 and then flip to page 2 and flip through the entire dictionary looking through that word for that word. Okay, with the dictionary, what you're probably going to do is open it up somewhere in the middle, figure out if the word you're looking for is past that or below it, and then take either the top or middle halves and then split that in half again and continue splitting things in half until you get to the word you're looking for. That idea is basically the idea of binary search. Okay, binary search is the best way to search a sorted list. And basically it works just like I talked about, repeatedly cutting the list in half by checking the middle of the list it is searching. Okay, so we'd find the middle, and then we'd find either the middle of the top half or the bottom of the half, then we'd find the middle of that quarter until we end up with our either value we're looking for and confirm it's not in the list. Okay, now the one trick with binary search, like we said, it's the best way to search a sorted list. Okay, performing a binary search on an unsorted list produces invalid results. In other words, it doesn't work if our list isn't sorted. So let's take a look at an implementation of binary search. Now I say an implementation because there's different ways we could write this code. We could perform it on arrays, array lists, 2D arrays. Okay, we could look for numbers, letters. Okay, here's just the simple version that goes through an array looking for an int. Okay, so we'll say binary search. We're going to search an int array called nums for an int called values. And our return is going to be the index of that value if we find it. Okay, the way it's going to work is we're going to find two values, low and high, the low starting as the first value in the array, and the high starting as the last value. Okay, the array.length -1. And then we're going to continue searching through a while loop, and we're going to continue as long as low is less than or equal to high. Okay, so as you can see here, we're going to be resetting high and low as we go through the list, and anytime low and high flip and get out of order, that's going to let us know when we're done, and that's going to return a -1, as in we didn't find the value. Okay, so while low is less than or equal to high, we're going to define another variable called middle, which is just the average of low and high. We'll then check and see if the nums at middle is equal to the val. In other words, if middle is our search target. If so, we'll return that index, we'll return middle. Or else what we'll do is we'll decide if middle is too high or too low. Okay, if the list at mid is greater than the value, okay, that means that the value is below mid, so we'll reset our high value to 1 less than the mid. Okay, or else, in other words, if it's our values, if mid's above the value, we'll reset the low and move that up to 1 above the mid. And as we go through that loop again, we'll redefine the mid within that half of the list, check and see if it's there, okay, check and see if we need to adjust the low or the high, and continue that way. So let's walk through a run of that binary search algorithm. Okay, and let's do that for this array I have here called nums with some values. And let's say our target value or search value is 8. Okay, walking through our algorithm, we're initially going to set the low and high to the first and last elements of the array. And then we'll find the middle, okay, by taking the average of the two, which in this case would be at element 14. If I go index 0 plus index 0, 1, 2, 3, 4, 5, 6, 7, 8. All right, 0 plus 8 is 8. Divide that by 2, that gives us a 4. That's why we're at index 4 here. Okay, at the 14, in other words. Okay, remember when I'm doing this, I am using integer division, so we're going to truncate decimals. We'll round down, in other words. Okay, so at this point, we're going to check if the value at nums at mid is equal to the value, 8. We'd return that. Okay, that's not. It's equal to 14. So or else, what are we going to do? Okay, if the value of num at mid is greater than the value, 8, we're going to adjust. Okay, in this case, it is. All right, 14 is greater than 8, so we're going to adjust our high value to mid minus 1. So in other words, high is going to move from the end of the list to 1 less than our mid value. Okay, and I'm going to continue this algorithm by now searching between my new low and high, so searching that half of the list here. So as you can see, in one step, I got rid of half the list to check. I don't need to check anything above my high now. Okay, so going through this list a second time, okay, going through our loop a second time now, again, we'll say mid is equal to low plus high over 2. In this case, low is 0, high is 1, 2, 3. Okay, so 3 divided by 2 is 1.5. In other words, 1. Okay, we'll go through that checking part of the loop again. Okay, we didn't find the 8, so we'll move on. Okay, this time our mid is less than the value we're looking for. Okay, 6 is less than 8. So in this case, what we'll do is we'll add to our low, or switch our low, we'll say low is mid plus 1. Okay, so my new low value now is 8. And now we're just searching basically 2 elements of the list between 8 and 10. Okay, so running through that algorithm one more time, we need to calculate our mid. Okay, index 0, 1, 2 plus 3. 2 plus 3 is 5. Divide that by 2, that'd be 2.5. Okay, integer division, that'd be a 2, 0, 1, 2, so that's why my mid is 8. Okay, we'll check and see, is nums at mid equal to value? In this case, it is. So that's why we're going to return 2 there. Okay, I'd encourage you to re-watch that part of the video if you need to. One of the big things you need to do with this algorithm on the AP exam especially is step through it step by step and determine kind of what part of the list you're searching and what the different variables are. But that's the basic idea of how binary search works here. Let's take a look at that algorithm in action one more time. And this time I want to take a look at what happens when we have a value that isn't in the list. In other words, in this case, value equals 25, which you can see here isn't here. Okay, same nums, same sorted list, just different target value. So once again, we have our low and high starting at the min and max. When we calculate the middle, we'll get the same thing. Okay, this time, first time up, value is greater than the middle, so we'll adjust our low value to be one more than the middle. We'll find the new middle, which is halfway between low and high, once again using integer division, and we get a 30. Okay, again, we haven't found it. This time through, our middle is higher than that value of 25, so we'll adjust the high. And now I have low equals high. Now this algorithm is going to keep running as long as low is less than or equal to high. Okay, why would we keep running when low and high are the same thing? Well, let's say I was searching for the 22. Well, then I'd have these variables here, and then my mid would be the 22. Okay, so we do need to go one more step. So we'll calculate a new middle. Okay, low is equal to high, which will be the same thing as middle. Okay, now in this case, we didn't find it once again, and if we check our conditions here, num at mid is greater than the value. Nope, it's less than. So we're going to adjust our low one more time. Low is going to become middle plus 1. And at this point, I've reached the stopping criteria for my loop. My loop's going to run as long as low is less than or equal to high. I'm now at the point where low is greater than high. The loop's not going to run, and a -1 will be returned, showing that we didn't find what we're looking for in this list. All right, so now that we've seen binary search in action, let's talk about how much better it works on a sorted list. Okay, remember, it doesn't work at all on an unsorted list, but if that list is sorted, how much more efficient it's going to be. Okay, typically when you're talking about efficiency for a computer program, you're looking at comparisons. So in other words, Boolean values to evaluate, okay, comparing one number to another. Okay, if you want to speed a program up, you eliminate the number of comparisons. Okay, and as far as maximum comparisons go, if we have a list of n items, okay, a linear search requires a maximum of n checks to find if an item exists in the list. Okay, so if we have, let's say, 100 items, at maximum, what we're going to have to do with linear search is go through and check every single one of those items, okay, to see if that item exists. Not a big deal with 100 items, but if we get into modern data sets with millions and billions, and there's probably some out there with trillions of items, you don't want to check things one at a time. That program is going to run all day long. Okay, binary search, on the other hand, requires a maximum of log base 2 of n checks to find if an item exists in a list. Okay, so for example, with that, so for n equals 100, log base 2 of 100 is equal to 6.6. Okay, meaning that if we round up, it's going to be a maximum of 7 checks to find if that item exists in the list. Okay, if we want to do that as mental math, okay, remember logarithms, just another way to write exponential equations. If I look at log base 2, or sorry, not log base, but 2 raised to the 6th power gives me 64. 2 raised to the 7th power gives me 128. Okay, if I want to get 100 checks in, I need to be above 100. Okay, 128 is the lowest exponent to a base above 100. Okay, so I have 7 checks maximum. Okay, another way you can think about that is how many times could I divide 100 in half and still have whole numbers? Okay, well that would be 7. All right, so that's kind of an easy way to check the maximum. again, that is a huge amount. Okay, let's say that number doesn't exist in our 100 list array, 100 item list or 100 item array. Okay, it's going to be a lot quicker just to make 7 checks to see if it doesn't exist as opposed to checking all 100 items. All right, that is it for binary search. As far as what you're going to be asked to do with that on an AP exam is basically what I have for you in the homework. You don't need to write this algorithm from scratch. I have a few problems we're going to fill in the blank for some variations just to see if you understand it. But the big thing will be thinking about what those different searching variables are as you loop through the binary search. And then also kind of looking at how it works, how many times it's going to run. I've got a few questions for that. Give the homework a shot, and like always, if you need some help, let us know. We're here to help you out.